The Committee on Science, Space, and Technology will come to order. Without objection, the Chair is authorized to declare recesses of the committee at any time. And welcome to today's hearing entitled Advances in the Search for Life. Before I recognize myself and the ranking member for an opening statement, let me explain that both Republican and Democratic caucuses are now meeting. For reasons you can imagine, those meetings are going long, and there is much discussion, which means that everybody here left their caucuses early, so I hope you will consider that to be a form of compliment. But we do expect more members to come in the future few minutes. I'll recognize myself for an opening statement. For centuries, humanity has wondered if life might exist elsewhere in the cosmos. Only in the last few decades have we been able to detect the existence of other worlds. 25 years ago, we didn't know that planets existed beyond our solar system. Today, we have confirmed the existence of over 3,400 exoplanets that orbit other suns, and we continue to make new discoveries. Today, we can observe planets that may harbor life. Earlier this month, scientists announced the first detection of an atmosphere around an Earth-like planet outside our solar system. This is a significant step towards being able to determine whether some form of life exists there. Last week, scientists announced the discovery of another Earth-like exoplanet in the habitable zone of a star 40 light-years away, close by in cosmic terms. It is a prime target for future investigation. Even within our own solar system, scientists have found intriguing possibilities of habitability. NASA recently announced the discovery of hydrogen gas and plumes shooting from the icy surface of Saturn's moon Enceladus. Organisms on Earth use hydrogen in a process to create nutrients. Perhaps simple organisms living near the moon's hydrothermal vents could use a similar process. Hopefully, NASA will find similar conditions when it sends a spacecraft to investigate Jupiter's moon Europa, where scientists have identified plume-like features. The United States pioneered the field of astrobiology and continues to lead the world in this type of research. Since its beginning, NASA has searched for life beyond Earth and has conducted numerous scientific investigations. Supported by NASA, the 2017 Astrobiology Science Conference is meeting this week in Mesa, Arizona. The theme of the conference is Diverse Life and Its Detection on Different Worlds. The NASA Transition Authorization Act of 2017, which President Trump signed into law last month, ensures continued American leadership in astrobiology and the search for life. It establishes the search, quote, the search for life's origin, evolution, distribution, and future in the universe, end quote, as a fundamental objective for NASA. To accomplish this, the bill directs NASA and the national academies to develop an exoplanet exploration strategy and an astrobiology strategy. The pursuit of evidence of life beyond our planet fascinates the American people. Programs like the James Webb Space Telescope and the Wide Field Infrared Survey Telescope, both of which the NASA Transition Authorization Act supports, will further advance our understanding of exoplanets and inspire the next generation of American explorers. We do not just look at places where life might be. We are laying the groundwork to go there. The National Academies highly recommended a mission to Europa. The Europa Clipper mission will greatly aid NASA's search for signs of life on Jupiter's moon. Private citizens, amateur astronomers, and non-government organizations also play an important role in our search for life. Private citizens and philanthropists fund organizations such as the SETI Institute, which searches for extraterrestrial intelligence. Citizen scientists conduct astronomical observations and analysis of vast astronomical data sets. Earlier this month, news came of a mechanic who used NASA data to help discover a new exoplanet system. This is a great example of citizen scientists at work. We should support more contributions from citizen scientists. It enhances public engagement and helps encourage the next generation of young students to pursue careers in astronomy, astrophysics, and astrobiology. It is human nature to seek out the unknown and to discover more about the universe around us. Many Americans often gaze into the beauty of the night sky in awe. We rightfully wonder if there is life beyond our pale blue dot. I thank our witnesses and look forward to hearing their testimony on recent developments in the field of astrobiology and the search for life elsewhere in the universe. That concludes my opening statement, and the ranking member, the gentlewoman from Texas, Eddie Bernice Johnson, is recognized for hers.
Thank you very much, Mr. Chairman, and good morning. Let me welcome our witnesses. Humanity's centuries-old quest to understand our place in the universe has gained significant ground in recent years. Geologists are uncovering evidence of the oldest life forms in Earth's geological record. The age of these fossils indicate that as soon as conditions were right on Earth, life appeared. That discovery raises profound questions. Has the same thing occurred on other bodies within and beyond our solar system? Is the genesis of life a common occurrence throughout the universe? Planetary scientists continue to find new environments within our solar system with the potential to harbor life. A key requirement for life as we know it is water, and the mantra for the search of life beyond Earth has been follow the water. Recent discoveries indicate that our solar system has an abundance of it. NASA's Mars Reconnaissance Orbiter discovered intermittent flows of liquid water on just below the Martian surface. The Hubble Space Telescope has sent back images of what appears to be intermittent water plumes and gushing from the surfaces of Jupiter's moon, Europa. And NASA Kasting mission has revealed evidence of hydrothermal activity in the surface water oceans of Saturn's moon, Enceladus, with indications of water on several other solar system bodies, including asteroids and dwarf planets and moons of Jupiter and Saturn. It appears that at least one condition for habitability is relatively common throughout our solar system. How do recent discoveries of water and habitable environments in our own solar system inform the search for life on planets orbiting other stars? NASA's Kepler mission has more than doubled the number of known exoplanets, bringing astronomers closer to finding an elusive Earth twin. The upcoming launch of the James Webb Space Telescope and the Transiting Exoplanet Survey Telescope will provide more opportunities to discover these systems and to uncover new ones. There appears to be many possible environments to search for life, both within our solar system and beyond. To narrow down the targets for research and exploration, scientists are working to understand fully how life originated here on Earth. The study of Earth's history, the early forms of life on Earth, and how the two evolved together is critical to this effort. And so the search for life truly is an interdisciplinary endeavor that draws our expertise in core science disciplines like biology, geology, chemistry, physics, and astronomy. The strength of these core disciplines is central to making maximum progress in search for life beyond Earth, and that's why we need to be committed to keeping America's research enterprise strong. We need to continue to invest as a nation in research and development, not cut back. I feel fortunate to be serving on the Science Committee at a time when progress is being made so rapidly in the search for life beyond Earth, and I look forward to hearing about that progress from our witnesses. With that, I yield back, Mr. Chairman.
Thank you, Ms. Johnson. And the chairman of the Space Subcommittee, the gentleman from Texas, Mr. Babin, is recognized for his opening statement.
Thank you, Mr. Chairman. Great to see everybody. Thanks for being here. The science of astronomy, astrophysics, and astrobiology expands mankind's understanding of our universe. It seeks to answer fundamental questions as to the nature of our universe, our place within it, and whether there's life beyond Earth. NASA has a long history of space-based astrophysics and astronomical science. Since the 1960s, NASA has operated space-based observatories. Among the most famous of these are the Hubble Space Telescope, which has produced some of the clearest images of the universe to date. Looking to the future, the James Webb Space Telescope, or JWST, set to launch in 2018, will be the most powerful space-based observatory to date and will be used to search for planets outside of our solar system that could harbor life. In my own district at Johnson Space Center in Houston, NASA's historic Chamber A thermal vacuum testing chamber is being used for end-to-end optical testing of JWST in a simulated cryo temperature and vacuum space environment. I'm proud to represent the hard-working men and women at Johnson Space Center contributing to JWST, our nation's next great space-based observatory. Johnson Space Center is also home to NASA's Astromaterials and Curation Office. This office is responsible for the curation of extraterrestrial samples from NASA's past and future sample return from future return missions. This is an exciting responsibility for Johnson Space Center and an important contribution in the search for life beyond Earth. We live in exciting times. The NASA Authorization Act of 2017 provides strong direction for NASA to continue to search for life and advance the science of astronomy, astrophysics, and astrobiology. It is quite possible that with continued efforts, humanity will finally answer the question and know definitely whether life exists on other worlds. I thank today's witnesses for joining us today, and I look forward to hearing your testimony, and I yield back, Mr. Chairman.
Thank you, Mr. Babin. And the gentleman from California, Mr. Barra, the ranking member of the Space Subcommittee, is recognized for an opening statement.
Thank you, Mr. Chairman, and thank you for holding this hearing on the advances in the search for life. That is a timeless question. The question, are we alone? Over the centuries, whether it's the child just on the grass looking up at the vastness of our universe to the most advanced astrophysicists thinking about this question. And that is exactly what we ought to be doing as a species, asking those questions. We're curious by nature. We're explorers. And if you think about what we're discovering and what we have discovered in recent years, from the deep oceans on the moons of Enceladus and Europa to the surface of Mars, the rapidity of finding inhabitable planets, vastly moves us forward to answering that question, are we alone? Now, what we may discover is not necessarily species that look like us, but what we may discover are those building blocks of life, looking for water, looking for organic molecules, looking for bacterium. But when that happens, and inevitably that discovery will likely happen in our lifetimes, the disruption that answers that question of are we alone is remarkable. If you think about 1997 with the Cassini space mission, we didn't know what we were going to discover. And yet, we're seeing plumes of spewing material from Enceladus, let alone flying through those plumes and discovering what we may discover. So we live in this remarkable time. The chairman and of the Space Subcommittee talked about the advances and discoveries of Hubble and Hubble's sibling that will launch shortly, James Webb. What that's going to allow us to discover about who we are, where we are, and where we go from here. Again, this is a remarkable time. The energy we saw this past weekend with thousands, if not hundreds of thousands of folks marching around the country in support of science. Around the world, in fact. These are discoveries that are not just unique to who we are as the United States, but to who we are as humanity. And again, I am encouraged by the chairman and the president's budget of the support for NASA funding and the support for continuing to explore and look for that next discovery. This is incredibly important. At the same time as we make those discoveries, it helps us better understand who we are as a planet on Earth, how we evolved, and where we may go next. So, as we move forward, as we start looking at NASA's 2018 budget, let's make sure we continue to fund that exploration externally, but we also understand NASA's multi-mission role here on Earth as well. That we continue to encourage the basic investments in basic science research in astrobiology and that search for life. And again, that we understand as we're going through the 2018 budget debate that we understand the impacts of cutting budgets, and we continue to support NASA's multiple role. So, I think this is a great time for this hearing. This is an exciting time in that search for an answer to the question, are we alone? And with that, I yield back. Yes, sure, I'll yield.
I just want to thank the chairman for this hearing. This is an exciting area, but the only definitive answer possible is the affirmative. we can never answer definitively that there's no life outside of the Earth. So that's one of our challenges, but nothing has the ability to capture the imagination and enthusiasm of people than the possibility of extraterrestrial life. So you all have the ability to really capture the American people's imagination and attention, and we need that now. We need people to be enthusiastic about science, so my hat's off to you, and I encourage you to do the best you can. With that, I yield back.
Okay. Thank you, Mr. Barrow. Let me introduce our panelists, and let me just say ahead of time that our hearings are always this bipartisan, but you're the happy recipients of not only great attendance, but great interest as well. Our first witness today is Dr. Thomas Zurbuchen, Associate Administrator of the Science Mission Directorate at NASA. Dr. Zurbuchen previously served as a professor of space science and aerospace engineering at the University of Michigan. He has worked on several NASA science missions, including Ulysses, the messenger spacecraft to Mercury, and the Advanced Composition Explorer. He earned both his Master's of Science degree and his PhD in physics from the University of Bern in Switzerland. Our second witness today is Dr. Adam Burgasser, Professor of Physics at the University of California in San Diego. Dr. Burgasser was awarded a 2017-18 Fulbright Scholarship to conduct astrophysical research and works with University of California San Diego Center for Astrophysics and Space Science. He contributed to the discovery of the TRAPPIST-1 system and currently conducts research in physics. He specifically investigates the lowest mass stars, coldest brown dwarfs, and exoplanets. He earned his Bachelor's of Science in Physics at the University of California, San Diego, and his PhD in Physics from the California Institute of Technology. Our third witness today is Dr. James Kasting, Chair of the Planning Committee of the Workshop on the Search for Life Across Space and Time at the National Academies of Science, Engineering, and Medicine. He also is an Evan Pugh Professor of Geosciences at Pennsylvania State University. He spent 2 years at the National Center for Atmospheric Research and 7 years in the Space Science Division at the NASA Ames Research Center. Dr. Kasting also chaired NASA's Exoplanet Exploration Program Analysis Group from 2009 to 2011. He earned his undergraduate degree in chemistry and physics from Harvard University and his PhD in atmospheric sciences from the University of Michigan. Our fourth witness today is Dr. Seth Shostak, Senior Astronomer at the SETI Institute. For 10 years, Dr. Shostak chaired the International Academy of Astronautics SETI Permanent Committee. Dr. Shostak has written, edited, and contributed to a half-dozen books on the search for life. His most recent work, Confessions of an Alien Hunter, details the history and scientific methodology of SETI. Dr. Shostak gives approximately 60 presentations annually and is the regular host of the SETI Institute's weekly one-hour science radio show, Big Picture Science. Dr. Shostak earned an undergraduate degree in physics from Princeton University and a doctorate in astronomy from the California Institute of Technology. We welcome you all, and Dr. Zurbuchen, if you'll begin.
I'm glad to. Mr. Chairman and members of the committee, this is an exciting time for exploration and discovery, and especially the search for life elsewhere. And I'd like to begin by expressing our gratitude for the committee's long-term support of our efforts in this area. In particular, we are pleased by the committee's inclusion of a provision in the recently passed Authorization Act that makes astrobiology and the search for life part of NASA's mission. We are not only committed, but also enthusiastic about accomplishing the objectives that Congress and the President have laid out for us. Furthermore, NASA is initiating work with the National Academies to develop science strategies for astrobiology and the study of exoplanets as requested. As part of our astrobiology effort, NASA supports research that leads to a better understanding of how life emerged and evolved on Earth, what conditions make any environment in our universe capable of harboring life, and what the potential distribution of such worlds are with life and beyond Earth. To fully engage in this pursuit, we need a convergence of many fields, biology, geology, astronomy, planetary sciences, earth sciences, and many other disciplines. Together, these researchers from these fields are exploring one of the greatest questions of our times. For example, just 2 weeks ago, NASA's Cassini mission confirmed the presence of hydrogen from plumes of Saturn's moon Enceladus, while our Hubble team announced the second observations of possible plumes on Jupiter's moon Europa. Both discoveries display the potential of life-enabling energy sources in oceans hidden away from our view beyond the icy crust, and a confirmation which would be very significant for this science. That's because scientists believe the plumes are spewing from cracks of these moons icy shells with material that are indicating of high thermal activity in their ocean floors. And we know from Earth that those parts of our world are spaces with lots of life. And while we haven't found definitive signs of life elsewhere just yet, our search is making remarkable progress, and astrobiology is the focus of a growing number of NASA missions. Mars 2020, our next rover after Curiosity, will continue to advance this search by investigating a region of Mars where the ancient environment may have been favorable to microbial life. Science instruments on the rover will provide high-resolution imaging and spectroscopy in many ways for characterizing rocks and soil from a distance. The Mars 2020 mission will also search for signs of past life, and throughout its investigation will collect samples that we hopefully can return in the future back to Earth, to the best labs we have. NASA is currently developing a Europa Clipper mission, which will conduct a detailed reconnaissance of Europa and investigate whether the icy moon could harbor conditions suitable for life. The promise of Europa Clipper is increasing by the day. If the potential plumes are linked to the subsurface oceans, studying their composition would help scientists investigate the chemical makeup of Europa's potentially habitable environment while minimizing the need to drill through layers of ice. Beyond our solar system, a transformation of understanding is taking place regarding planets around other stars, exoplanets. I was in grad school when the first planet orbiting another star was announced. I still remember it vividly, the day, the moment when I learned about this. It was so exciting. And that was just the beginning of an avalanche of discoveries. You mentioned we have close to 3,500 such planets found and discovered elsewhere, and billions more are waiting to be revealed in our galaxy alone. This February, NASA's Spitzer Space Telescope team announced the discovery of 7 Earth-sized planets, the most ever found around a single star, TRAPPIST-1, and I'll leave it up to you to kind of fill in the details. It's just really exciting, and discoveries are coming out by the day on this one. NASA's Spitzer, Hubble, and Kepler space telescopes will continue to help astronomers plan for such follow-up studies using NASA's upcoming James Webb telescope launching in 2018. With much greater sensitivity, Webb will be able to detect the chemical fingerprints of water, methane, organics, other important molecules that really are related, we believe, to lives, and the factor that help us assess whether these worlds have an ability to harbor life. With all this activity related to the search of life in so many different areas, we are on the verge of one of the most profound discoveries ever. Thank you.
Thank you, Dr. Zurbuchen and Dr. Burgasser.
Thank you, Chairman Smith, Ranking Member Johnson, and esteemed members of the committee. It is an honor to share with you today recent discoveries and future opportunities in the search for potentially habitable worlds and life among the smallest stars. I speak today as a representative of the international team that discovered the 7-planet system around the star TRAPPIST-1, a system that harbors as many as 3 potentially habitable Earth-sized worlds. This and other recent discoveries represent the beginning of an era of exoplanet exploration that, in the next 5 to 10 years, will allow us to identify truly habitable worlds and possibly life beyond Earth. These transformative advances, addressing one of humanity's most persistent questions, are we alone?, are fully achievable through a diverse portfolio of research programs led by U.S. scientists and supported by federal funding to NASA, NSF, and other science agencies. Slide, please. Today I will focus my testimony on the opportunities afforded by the lowest mass stars. When we look up in a clear night sky, most of the stars we see are hot, massive, and distant. This visual sample does not reflect our Milky Way galaxy's actual stellar population, which is dominated by cool, low mass, and dim stars, barely perceptible even with the largest telescopes. Next slide, please. These low-mass stars outnumber Sun-like stars 5 to 1 and include some of our nearest stellar neighbors, many discovered just in the past 5 to 10 years thanks to deployment of advanced infrared array detector technology and missions such as NASA's Wide Field Infrared Survey Explorer. The search for potentially habitable worlds around these stars is a search for terrestrial planets with surfaces on which liquid water can persist. Such planets reside in the Goldilocks habitable zones around stars, not too hot, not too cold. For low-mass stars, this habitable zone can be up to 20 times closer to the star than Earth is to the Sun, which makes such planets easier to find and easier to study. Next slide, please. Thanks to public investment in technology, facilities, and people, this search has borne fruit. In 2014, the NASA Kepler spacecraft team reported the discovery of Kepler 186f, the first Earth-sized world in the habitable zone of another star. Work led by my former classmate and San Diego native Dr. Lisa Quintana, now at NASA Goddard. Just last year, it was announced that the nearest star to our sun, Proxima Centauri, has a super-Earth planet orbiting its habitable zone. Next slide, please. The University of Puerto Rico at Arecibo's Planet Habitability Lab tabulates 12 very likely habitable worlds identified to date, all of which orbit stars less massive than the Sun. Next slide, please. The discovery of the TRAPPIST-1 system is a capstone to this endeavor and an example of how partnerships between universities, government agencies, and international collaborators can produce truly transformative results. TRAPPIST stands for the Transiting Planets and Planetesimal Small Telescope, a facility operated by the University of Liège, Belgium, and led by my colleague, Dr. Michael Guillaume. And I should say TRAPPIST is also the name of a popular Belgian beer. This facility is relatively modest, a robotic telescope with a 2-foot wide mirror, optimized for the search of planets around the lowest mass stars. Even the stars are modest. TRAPPIST-1 is only 8% the mass of the Sun and is about the size of Jupiter. Yet our international team, which includes scientists, students, and engineers from 24 institutions in 11 countries on 5 continents, including U.S. researchers in the states of California, Maryland, Massachusetts, Texas, and Washington, were able to mobilize our shared resources to make this exciting discovery. Next slide, please. Key to our success was NASA's Spitzer Space Telescope, America's flagship infrared space facility, that monitored TRAPPIST-1 for 21 days, revealing this amazing light curve. Each dip you see is one or more of the planets passing between the star and us, dimming the starlight by less than 1%. We detected 92 transits associated with 7 planets, all around the size of the Earth, with orbital periods between 1.5 and 18.8 days. The planets in this compact system fit easily within the orbit of Mercury and are so close that they gravitationally tug each other, causing measurable variations in their transit times. Such a compact system would be cooked if it was in our solar system, but around a cool star like TRAPPIST-1, 3 of the planets, E, F, and G, orbit within the star's habitable zone. With 3 chances for a habitable world, the TRAPPIST-1 system is one of the most promising to date in the search for life beyond the solar system. But all indications are that this is just the tip of the iceberg. Chairman Smith mentioned the discovery of a super-Earth around the habitable zone of a nearby star by the NSF-funded M-Earth project, and this will be joined by a space-based project, TESS, in the next year that will expect to discover hundreds of stars around other planets. Our generation is the first in human history to know that there are worlds beyond our solar system. Will the next generation know whether life exists on those worlds? We have the opportunity and responsibility to continue our nation's legacy of exploration and discovery so that our children and grandchildren can search for life in new ways.
Thank you, Dr. Burgasser and Dr. Kasting.
Chairman Smith, Ranking Member Johnson, and members of the committee, thank you for allowing me to testify at this hearing. I was selected for this spot because I chaired the planning committee for the recent National Academies workshop on searching for life across space and time. In my written testimony, I've attempted to summarize key points made by various participants at that workshop. Here I will focus on 2 important new discoveries, one within our solar system and another outside of it. I should emphasize that I'm speaking on my own behalf as an active researcher and not on behalf of the National Academies. The new solar system measurement was made by NASA's Cassini spacecraft, which has been orbiting Saturn for the last 12 years. Chairman Smith already mentioned this. One of the objects that Cassini has studied is Saturn's moon Enceladus, which is shown on this slide. Enceladus is of great interest to astrobiologists because, like Jupiter's moon Europa, it's thought to have a subsurface ocean. Part of the evidence for this ocean is a plume of material emanating from Enceladus' south pole. During its lifetime, Cassini has performed multiple passes through this plume, sampling the gases that make it up. Previous measurements had already determined that the plume consists mainly of water vapor with smaller amounts of carbon dioxide and methane. As many of you already know, NASA is about to bring the Cassini mission to an end by plunging the spacecraft into Saturn sometime late this summer. With the end in sight, flight controllers have been taking more risks with the mission over the past 2 years. In 2015, Cassini made its deepest penetration yet through the plume, passing within 49 kilometers of the Moon's surface. The mass spectrometer was also operated in a different mode that allowed it to measure molecular hydrogen. This, in turn, allowed researchers to estimate the amount of chemical energy available within Enceladus Ocean from the reaction between carbon dioxide and hydrogen to make methane. This reaction is used by methanogens here on Earth to power their metabolisms. The new results indicate there should be more than enough chemical energy available within the ocean to support methanogens. This, of course, does not mean that life is present on Enceladus. However, it suggests that the search for life there could be rewarding. Next slide, please. My second update concerns rocky planets that have been discovered orbiting within the habitable zones of nearby red dwarf stars, also known as M stars. Adam Burgasser just told you about the planets orbiting TRAPPIST-1 and about the other new exoplanet announced last week that orbits this M star LHS 1140. All of these planets were discovered from the ground by looking for transits in which the planet passes in front of its parent star. During transit, some of the starlight passes through the planet's atmosphere, allowing its composition to be studied spectroscopically. This has been done previously for giant planets using the existing Hubble and Spitzer space telescopes, but it will be done much more accurately by NASA's upcoming James Webb Space Telescope, JWST, which launches late next year. The hope is to look for the presence of possible biosignature gases, especially molecular oxygen, O2, which is produced by photosynthetic plants and algae here on Earth. A third new exoplanet discovery announced late last summer, which you also have heard about already, is a rocky planet orbiting within the habitable zone of the nearest M star, in fact, the nearest star, Proxima Centauri. This planet was discovered from the ground by a team of European astronomers using the radial velocity method. This technique uses the Doppler effect to look for the back and forth motion of the star caused by planets orbiting around it. Because the Proxima Centauri planet probably does not transit, it is harder to study with JWST. The planet is close enough, however, that it can potentially be characterized from the ground using planned 30 to 40 meter telescopes. By again using the Doppler effect, researchers can separate the absorption lines in the planet's atmosphere from lines formed within the Earth's atmosphere, allowing them to look for biomarker gases such as oxygen and ozone. Ultimately, astrobiologists would like to look for Earth-like planets orbiting stars more like the Sun. This will require large space-based direct imaging telescopes that have not yet been approved. The good news is that NASA is again studying them. Hopefully within the next 15 to 20 years, we'll be able to search for habitable planets and life around all the stars within the solar neighborhood. Thank you again for allowing me to testify at this hearing.
Thank you, Dr. Kasting and Dr. Shostak.
Chairman Smith and members of the committee, thank you very much. I'm going to talk about the search for intelligent life. Unlike what you're likely to find under the icy crust of Enceladus, there may be life there. There are 6 other places in the solar system where you might find some biology, but you'll need a microscope to see it, and it won't hold up its side of the conversation. All right, let me just say that in the 21st century, there are 4 things that I think are going to be very important that will be remembered 1,000 years from now. One, we're finally understanding biology. That's going to lead to interesting questions like, curing a lot of disease, but also designer babies. Second, we're going to be moving into space, something that it doesn't sound so attractive if you're going to go to the moon or Mars, not great places, but if you're in orbiting space colonies, great, and it's an inoculation against self-destruction of the human race here on Earth. If we wipe ourselves out, not to worry. There's still some humans in space. The third thing we're doing, and this is probably the most important, is inventing our successors, generalized artificial intelligence. The head of the AI operation at Stanford only a couple of years ago. I asked him, will we have a machine that can write the great American novel by 2050? He looked up at me and said, yes, then went back to sleep. Okay, the fourth thing that we're going to do is find life in space, and that's philosophically important. It might be important in other ways, but at least philosophically. So how are we looking for life? You've heard the presentations here. There are three ways. There's a three-way horse race. One, we just go there and look. That's exploration. We go to places like Enceladus with spacecraft, grab some of that stuff being shot into space, bring it back, look at it under a microscope. Go to Mars, look around Mars. As I say, that's where all the big money is. That's where NASA spends its money and the other space agencies around the world. The second thing to do is build space-based telescopes that can sniff the atmospheres, sniff the atmospheres of planets around other stars, and Dr. Kasting has already alluded to that. Again, that's hundreds of millions of dollars. It's something we can do in the next 10 years. And the third thing to do is what's called SETI, where we try and eavesdrop on signals being broadcast by other societies that at least have technology that would allow them to do that. That's where I work. There is essentially no federal money for that. All right, let me talk a little bit about that. How do we go about that? What's different in the last 5 years? Certainly the types of objects that we're pointing our antennas at. In the old days, we would look at stars sort of like the sun, because we know that stars like the sun at least have a planet where we have intelligent life. And I leave it to you to determine what's intelligence. In our field of work, if you can build a radio transmitter, you're intelligent. You can ask the guy next to you whether he can do that. The second thing that we are doing is improving the equipment. Okay, so let me just give you an idea. The TRAPPIST-1 system has been mentioned here a couple of times. If you were in the TRAPPIST-1 system on one of those planets and you looked up at the sky, you would see, some of those other 7 planets, and they would be big. They would be balls in the sky. You go out tonight, look to the east, and you'll see Jupiter, but it's just a point of light. Not true in TRAPPIST. You actually see them. Whereas it takes 7 months to send a rocket to Mars, you could go from one TRAPPIST world to the next during the course of a weekend. What all this means is that there are, to begin with, more planets in the TRAPPIST-1 system that could cook up life. That means more chances to win the lottery by cooking up life. And as soon as you've done that, that life will spread to the other worlds. And it will spread because meteors will slam into one planet with life and carry bacteria or whatever to the next world in just a very short period of time. So it will infect all these worlds. If there's any intelligent life in the transit system, that will have colonized essentially all these worlds too. So this could be a mini federation of planets, if you will. This is not just another world with life. This is an ecosystem there, okay, if there's any life. We are using our Allen telescope array to look at the TRAPPIST-1 system, and we're using a situation in which we wait for the planets to line up and see if there's then any difference in the amount of radiation coming our way. Because at that point, you're looking down the communication pipeline between these planets. Finally, let me just say something about the technology. This experiment will only succeed if we can look at about 1 million or so star systems. That would have taken thousands of years with the current technology. Thanks to improvements mostly in computers, that is speeding up by orders of magnitude. Over the next 20 years, we will be able to look at about 1 million other star systems, and I bet everyone a cup of coffee that we'll find something. I may have to buy a lot of coffee. Let me just conclude by saying the funding for all this is very limited. It's all private funding. There is no government money for doing this. Even though finding intelligent life would have the greatest impact on humanity, there's no federal funding. And the total number, as a consequence, the total number of people that work on this problem in the entire world is far fewer than the number of people sitting in the back row in this room. Thank you very much.
Thank you, Dr. Shostak. Thank you all for your fascinating testimony, and I'll recognize myself for questions. And Dr. Shostak, let me address a first comment and then a question to you. The comment is this. I want to, I think, for the first time, publicly thank you for exposing me about 2 decades ago to SETI's methods of looking for the search for extraterrestrial intelligence when we spent what seemed like a long night at Arecibo. But that was my first real exposure, and it sort of set me on the track to be continually interested in this subject. So thank you for that. A couple of questions. One is just to read from part of your written testimony. If we conjecture that there are 100,000 signaling societies in our galaxy, then we will have to scrutinize roughly 1 million star systems before detecting a transmission. This is approximately 10 times the total sample of all SETI experiments undertaken since 1960. So we're just beginning the process. We have a long ways to go. You mentioned all the different ways we might search for extraterrestrial intelligence. What do you think is the best current method being used? And is it radio? Is it laser? What might it be? And what do you recommend?
Yeah, well, it's obviously hard to forecast what to do to succeed. Be like asking Captain Jim Cook, 2 weeks out of England, what part of the Pacific is best to search for new islands. Obviously, we don't know. But the radio search is, that's following a trajectory in terms of improvement that's very easy to predict because it follows Moore's law. It just follows computer technology. And so we know that over the course of the next 2 decades, that will get at least 100 times faster and maybe more. So I have a dog in this fight. I seem to think that is a good way. But I have to say, we're also developing schemes for looking for flashing laser lights in the sky, right? If some society out there is sending a laser beam here, a thousandth of a second long, once every 2 weeks, nobody on Earth would ever know. We wouldn't know that. And it's worth looking for that because, indeed, except for the transmissions we've been broadcasting into space since the Second World War, there's no way that the aliens could know we're here. If they're more than 70 light years away, they don't know that Homo sapiens exists. So maybe they just ping us intermittently.
Right.
See if anybody's home.
Okay. Thank you, Dr. Shostak. Dr. Zurbuchen, let me ask you the next question, which is our Authorization Act that we just signed into law last month directs NASA to search for life in the universe, any form, any kind. How will NASA implement the directive in the NASA reauthorization bill?
Thanks so much for the question. First of all, there's a number. You should know that with me at the leadership of the Science Mission Directorate, this is one of the top 3 priorities that we're focused on. So kind of a high-level priority that we use to integrate research across the disciplines. So the way we'll look at it is in an interdisciplinary fashion, first of all. The second one is to recognize that we already have a series of missions that are in development. We've talked about them here, trying to really deploy them in a strategic fashion. We're looking, of course, at the Academies' input and prioritization to help us with that, because we think the Academy is exactly the right, like you directed, exactly the right voice for us to really exploit these assets the right way. Also, as we go forward and look at decadal guidance from other disciplines as they come forward, we expect that we'll also develop perhaps new technologies, new assets that will help in that search.
Okay. Thank you. Dr. Burgasser, you mentioned that the most common type of star in our galaxy are the red dwarfs, which you study, and those were fascinating slides you put up. What is the likelihood that we will find life near a red dwarf star?
That is a very challenging question. I can only address that these red dwarf stars have a lot going for them in the terms of being able to search for life on planets around them. They are the most numerous. They're also the nearest stars to our sun. It turns out that there are more terrestrial planets per M dwarf than sun-like star. There are about 2 terrestrial planets on average for all of these low-mass stars. And the ability to measure their atmospheres is enhanced by their small sizes, the star's small sizes. Now, there are things that are not going for small stars. These planets are very close to their star, so they are tidally locked. And we are still trying to understand what effect that could have on the climates of these planets. And they're also exposed to higher magnetic storms, the kind of magnetic storms we get from the sun, but actually much more powerful because they're closer to their stars. And that may or may not have positive or negative implications for the development of life on these planets. So these are active questions because we've only just started finding these planets. We are really approaching this from both theoretical and observational perspectives to understand what we might expect to find. But of course, the best thing to do is to actually find this evidence, and then we can provide an answer.
And go from there. Thank you.
Yeah.
Let me squeeze in a last question, maybe direct it to Dr. Zurbuchen and also Dr. Shostak. Should NASA consider, and I think there's appropriate language in that authorization bill, should NASA consider contracting out with organizations that might be searching for their extraterrestrial intelligence? But there's a
Well, I
little
think
bit
my
of,
answer is a foregone conclusion.
yes, I
of
just
course.
going to say.
Yes, no, I think so, and for several reasons. One, of course, it would be more interesting to find it, I think, than find it. With all deference to the astrobiologists here, I think it would be very interesting, particularly to the public. The public's very interested in life, but mostly in the intelligent variety. I make that statement without numbers here, but I think that's true. And the other thing is it would be philosophically very consequential. There are other possible sequelae. You could indeed maybe understand something they're saying, in which case you're in touch with a society far more advanced than ours. I don't know what the consequences of that might be. I don't even think that it's very likely we would understand anything. But simply to know you're not the only kid on the block, I think is that's exploration that I think is worth doing.
Okay, thank you, Dr. Shostak. The gentlewoman from Texas, the ranking member, Ms. Johnson, is recognized for her questions.
Thank you very much, Mr. Chairman. I guess I will point this question to each of the panel members. How important do you think the sustained federal support for research of core science disciplines such as the biology, geology, chemistry, physics, and astronomy to the success of interdisciplinary fields of astrology? And to what extent would the budget cuts have on the impact of this research that's in progress now for Search for Life? What are the challenges to us?
Let me answer the first part of
Okay.
your question, which is how important is it? And I really do believe that to answer this question, is there life out there, is really a confluence. It's not a yes/no kind of answer. I mean, kind of the way to think about that is not that. It's really opening up a new area of research with entirely new research questions that we've never seen. The way we do answer these questions, each one of those questions, whether it's hydrogen and the blooms of Enceladus, relates to fundamental science that is underlying that. So how important is it to have this fundamental science? It's essential. It's the tools we use in every one of those questions to actually unlock the unknown.
And so I will echo your comment that this is a fundamentally interdisciplinary nature. I'm actually teaching a writing course. I'm going to give a shout out to my students who have to watch this next week. We bring together areas across the science disciplines, but also beyond the science disciplines. Congressman Barra mentioned that this is a disruptive question that we're asking, are we alone? And so it doesn't just touch on science, but also touches on philosophy, legal issues, all kinds of issues. So at its core, we really need to have a very broad-based knowledge sort of system to understand both the question and also when we answer that question, what does it mean for humanity?
If I could just add that, of course, you need the support of the basic sciences at the basic level, but we're also seeing the need for more coordination between planetary science and astronomy, because those used to be, they are two separate divisions within NASA, but with exoplanets we share a common goal of understanding those planets. And so, you know, I've been happy to see that the two divisions in NASA have been talking to each other, and I think that's very important in making progress in the future.
Well, I support what has been said here. Clearly, it is interdisciplinary, and it's also exciting science. It's also comprehensible science to Mr. and Mrs. Front Porch, if you will. If you ask your neighbor, hey, what do you think about the Europeans spending billions of dollars to find the Higgs boson? That's fundamentally important, but I doubt that they understand what it's about, nor do they probably want to spend that kind of money. I don't know. But this is exploration. When you talk about astrobiology, it's something everybody understands right away. It's also exciting science. And not to do it, I mean, it would be like if you're a European country in 1500 and somebody says, do you think it's worth investing in some ships and some crews and send them around the world and see if we can map the globe? Obviously, it was worthwhile.
Thanks to all of you. Of course, research to me is the door to the future. My concern is that each year we go through whether we're going to cut back on NASA research. And I wonder whether this will have an impact to focus more strongly on this. I don't want to either or, but it seems that that to do another is to neglect the other. How do you think we can continue forth with both bodies of research, and what is the importance?
I'll take a stab at that.
Yeah.
You know, I think we have to listen to our citizenry and understand that these are questions that excite, inspire, and drive interest not just in astronomy but across STEM fields, and keeps us competitive at the world stage. And so an investment in NASA is going to have incredible returns down the road across all fields of technology, of biomedical science, of new materials. And you know, I leave it up to your esteemed colleagues, you know, to decide where these budgets
It's
land.
dangerous.
But it is certainly critically important to realize that this is investment in our future on many levels.
Thank you very much. We've learned so much, and I want to see it keep going, but I am concerned. Thank you.
Thank you, Ms. Johnson. And the gentleman from Louisiana, Mr. Higgins, is recognized for questions.
Thank you, Mr. Chairman. Dr. Shostak, it's been stated for decades that some species of cetaceans, whales and dolphins, are recognized for their intelligence. Would you agree with that general assessment?
Yeah, well, clearly they have a higher encephalization quotient. That's a lot of Greek, but what it means is their brain volume relative to their body volume is higher than any other critters on this planet, other than, you know, our simian friends and ourselves, right? So by that measure, they are clever. They also can recognize themselves in a mirror. They know that when they look in a mirror, they're seeing themselves, something your dog can't do, right?
Is it generally accepted that these creatures have a means by which to communicate with each other?
There are people who think that. I'm not one of them. I knew John Lilly a little bit, and Gerard Verschuur is another guy who thinks that the cetaceans can communicate by, in the latter case, ESP. I think that there's a great experiment being run that disproves the notion of ESP. It's called Las Vegas.
And I would agree with you there. But they do vocalize, do they not?
They do, and in fact, sort of a statistical analysis of the sounds that they make show, or at least seem to indicate, that it's a language. It's not just, you know, barking, if you will. So yes, they are clever, and they're quite clever, but you will note that their level of technology leaves something to be desired. That may be partly a consequence of living underwater, where it's hard to smelt metals and so forth and so on. But I don't think that the cetaceans are comparable to humans.
I bring this up because a research scientist by the name of Lawrence Doyle at the SETI Institute has studied information theory and patterns in animal communication as means of understanding how to detect signals from the noise we hear from space. And I'd like your comment on that. Within your comment is my own personal consideration that should intelligent life ever be discovered, whether or not that's, you know, a realistic perspective is subject to debate, I'm sure. But should intelligent life in the cosmos ever be discovered, if for decades we've been unable to communicate with dolphins and whales, how shall we ever expect to communicate with intelligent life if it would be discovered across the cosmos? And how does that relate to Lawrence Doyle's research?
Yeah, well, I certainly agree that the fact that we can't communicate with any other species on this planet may indeed incline you to think that we would never be able to find it elsewhere. I think what it might show is that we might not understand anything being sent, but you know, the way we do this experiment is not by listening for patterns in any signals, messages. Here's the value of pi. Here's the Fibonacci series if you're a Dan Brown fan. None of that. We are simply looking at the nature of the signal, the kind of signal that transmitters make, without regard to the message. The message would be much, much harder to find in any case, the bits. So what language they use, if they use any language, how they've encoded their information, the things that separate whale communication, for example, from human communication. That's sort of, if you will, literally below the radar. So what we are doing is just to try and find the technology they've used. This signal is due to a transmitter. What they're saying is not something we'll know right away, maybe ever.
And that would describe Lawrence Doyle's work? That's
Yeah, he's interested in finding out, if you have a big brain, do you start using language? At what point do you start using language? I have to say that he has found these statistical indications that the dolphins are using language. Also, in many other species, he claims, even in ants. I have to say I've never been impressed by ants' intelligence, but on the other hand, maybe they're not impressed by mine.
I think that's an excellent note to yield back, Mr. Chairman.
Thank you. Thank you, Mr. Higgins, and the gentleman from California, Mr. Bear, is recognized.
Thank you, Mr. Chairman. This is a great hearing, right? I mean, it is a seminal question, particularly, again, if we want to stimulate our next generation to really get interested in science. I mean, it's very easily understandable, as you suggested. It's not Higgs boson. It's, are we alone? That search for life, which any student can grasp, and any individual can grasp. And it opens up philosophy, it opens up, humanity, et cetera. Dr. Shostak, you talked about 3 different methods, direct exploration, space-based telescopes, or looking for signals. I don't think it would, it's either or, right? These are all complementary modalities that work off of each other and feed into the body of knowledge. Given the vastness of space, and my question would be, we don't have the funding to do everything and look at every piece of information that's coming in. So some of, with the internet and the interconnectedness of the world now, is that citizen scientists, those citizen astronomers. What are some thoughts and ideas of how NASA and other agencies, including SETI, can use that, that massive humanity in a strategic way to get folks to look for those signals or look at the vastness of space, but then also to encourage our young people, so classrooms of students might actually be part of this search for life. We'll start with you.
So I agree with your notion entirely, and also that there are opportunities and that we can do that. Like, one of the coolest things when I was doing my PhD on a different continent, my computer at night was working for his organization with SETI at home, right? Because my computer was tied in. I did, so many of my colleagues basically gave our CPU power away for that. I think right now we have many opportunities. Whenever Juno flies by Jupiter, there's thousands of people the next day taking the new imagery, of all ages, children of all ages, taking the imagery with wonder and turning them into art, really analyzing them, sometimes actually finding exciting science in doing so. So at NASA, we're really excited about these citizen science type of projects, and we actively look for collaborations in areas also where currently through our decadal process and otherwise our funding emphasis is not high. You should know that last week I was in a meeting, I think with you. We were in a room, where we talked about all aspects of search for life. And again, every time we come back, we want to, as we make progress, we look at it again. Are we putting the money at the right place? The reason we're so excited about search for life right now is we're really driving up the S-curve, that the slope is enormous right now of the progress we're making. And this is one of the most fruitful, really civilization scale questions we can address. So that's why we're so excited.
Dr. Burgasser.
Yeah, thank you for asking that question. I think it is important to recognize the decadal process in this is one of the ways that we as scientists, a very diverse group of scientists, come together and identify what are the sort of main ways that we can address some of these outstanding questions. And that's an important process because it's a competitive process, but it's also a consensual process. And so we kind of come together on this. I wanted to touch on your engagement with the community in terms of the science itself. And certainly the citizen science programs such as Planet Hunters and Exoplanet Explorers, background Ground World, SETI at Home, have engaged a lot of the public to this work, and they have contributed to the discoveries, and that's one of the amazing accessibility parts of this this kind of research. But I should also say that the importance of this work being publicly funded also means that the data and the research that we produce is immediately available to the public. And I have been able to work with a diverse group of students from minority-serving schools, from low-funded schools in San Diego, and researchers across the world to actually work on the raw data to find these planets. And so that's one of the ways that we really engage the public at large, is that they can actually really do the research because they are using data that's funded by the public.
Great. Dr. Kasting.
Yes, I think it's been great that the public has been able to get directly involved in SETI, and I think that's generated a lot of interest. SETI, as I said in my written testimony, SETI got started before the search for simple life because the technology is actually simpler than the search for simple life. And you know, it's more difficult to get the general public directly involved in the search for simple life because you need big space-based telescopes and big ground-based telescopes. So there's a role for the public, but there's also a role for government in the search for life.
So it looks like I'm out of time, but Dr. Shostak, if you want.
Yeah, thank you. Oh, go on.
Oh, well, just one thing. First, I'm slightly embarrassed. SETI at Home is not our project. It's the University of California, Berkeley. But here's something that hasn't been mentioned, and that is the National Academy of Sciences has recognized that a very high percentage of people who go into science because of what they've seen on television and in the movies. And so they have a project. They have an office down in Irvine, California, near Hollywood. And they, in fact, whenever they hear of a new film being made about space, they will bring in some scientists to try and get the science right. Personally, I don't think that makes any difference in the appeal. But the facts are that that sort of informal exposure to science has a tremendous effect.
Fantastic. Thank you. I'll yield back.
Thank you, Mr. Barra. The gentleman from Florida, Mr. Posey, is recognized for his questions.
Thank you very much, Mr. Chairman. Dr. Zurbuchen, we often characterize investments in basic scientific research as paying off in technical advances that will eventually impact our day-to-day lives here on Earth. Can you point to some recent examples of breakthroughs in the astrobiology field that have had that type of impact?
I am sure there are examples, and I will return with questions for the record. I can give you examples that I encountered just recently in astrophysics in general. For example, look at some of the mirrors that were developed for X-ray optics that relate to this research. Mirrors that are, of course, grazing incidence mirrors that are done at Marshall in Alabama. And these mirrors are subject of tremendous interest from the biomedical space because of the fact that, of course, we want to focus X-rays also in medical application and spin-outs of a variety of, characters or foci can be formed with that. They're in negotiations right now, so there's not a big company right there. But we have ample ones of these, stories that are forming around our research, and that's also why we're so excited about it. I've been part of hundreds of startups in my previous job as an innovation leader at the university I worked before, and I really believe in it. But I will get back on good examples that are recent and are related to this.
Okay. Thank you. Any of the others care to comment on what you see coming from research in the next 3 to 5 years?
Could I just take a stab at that? I don't actually know practical things that come out in the next 3 to 5 years, but my colleague Sarah Seeger at MIT, who's an astronomer, sometimes calls the search for life the second Copernican revolution. And so Copernicus figured out that the Earth goes around the sun rather than vice versa. We are looking to see whether we're alone in the universe and whether life is common. And, I'm not sure there were practical things that at the time that came out of the Copernican revolution, but nevertheless it changed mankind. And so could this search.
Might also point out in 1920, if you talk to physicists that are worried about quantum mechanics, and they themselves would have said there's absolutely no practical application of any of this, and now everybody carries quantum mechanics around in their pockets.
Well, we just had to march for science all over the world, and Of course, a lot of people think there's only one answer to all scientists and all science, and that's whatever they think. And I remind them that until Galileo, 100% of the world's scientists swore the Earth was flat. And you have to ask those questions. You have to question what some consider as fact. Thank you, Mr. Chairman.
Thank you, Mr. Posey. And the gentleman from Virginia, Mr. Byer, is recognized.
Thank you. Mr. Chairman, thank you for holding this very bipartisan hearing. It's very exciting. And thank you all for being here. Dr. Shostak, I was reading about METI, rather than SETI, the messaging to extraterrestrial intelligences. And one of the things they said was they said that we were not a communicative civilization because we don't practice such activities as purposeful and regular transmission of interstellar messages. Should we be a communicative civilization?
Well, that's really up to you. I mean, there are people who think that we ought to take the initiative, send signals into space, and see what comes back, if anything. I point out that this has been done in the past, mostly as demo experiments, as you know. I mean, even the records on the Voyager spacecraft and the plaques on the Pioneer spacecraft are designed in case any Klingons ever pick these things up, which they never will, but they get a greeting card from Earth. I don't agree with those who think that this would be dangerous. There are people who say that. Even Stephen Hawking has made that comment, because you obviously tip off the aliens that were here, and who knows what they really are like. Obviously, we don't know anything about alien sociology, and maybe they just come to Earth and incinerate the planet on a bet. I don't worry about that personally, but you might say that's not good enough. They simply point out that we have been transmitting into space willy-nilly since the war. And mostly, yes, TV and FM radio, but it's mostly radar. It's mostly radar. So if you're paranoid and you're worried about this, if you think maybe it's not a good idea to let anybody who's out there know that we're here, then you better be prepared to shut down the radars at Reagan Airport. And I don't think you want to do that.
You mentioned the 70 light years as sort of is that because that's when radar and the television started?
Yes, and also FM radio. But yes, radar, television, and FM radar, and radar are the things that that go out, they go right through the ionosphere. And radar transmitters tend to be very powerful. If you were looking at the Earth from one of these nearby planets that we've talked about here, and you had a big antenna, as big as this building, you could pick up our radars.
You've mentioned a number of times the philosophical and theological consequences of discovering life. And obviously there's lots and lots in the science fiction literature and films and stuff about how people react, overreact, go crazy. Are there philosophers or theologians thinking about this, writing about it, trying to anticipate what it would be like?
There are. There's a lot of research, and normally what they do is they try and look for an historical precedent for this. I guess it's sort of lawyerly to do that. And they say, okay, what in history has happened that would give us some clue to what the public's reaction or organized religion's reaction would be? But there is really no very good precedent for this. When I tell people at cocktail parties, not that I get invited to many, but if I tell people, what I do for a living, they'll frequently ask, well, if you found a signal, you wouldn't tell us. The government would shut you down, right? And I said, the government doesn't even know what we're doing. I don't think they would shut us down. We've gotten false alarms in the past. Government wasn't interested. My mom didn't even call. Nobody was interested, okay? Only the New York Times, they were interested. So, but they think that the public couldn't handle this news. I think that is totally false. If you were to pick up a newspaper, you won't do that. Open your browser tomorrow and find news that we'd found a signal coming from 800 light years away. I doubt that you would say, I'm not going to work today, I'm going to riot in the streets.
We ran SETI at home for years with my kids and all the different computers, and now we're looking for Riemann prime numbers, I guess, because the SETI thing is shut down.
We could always use more prime numbers.
Yeah, we haven't found any prime numbers yet either. I've talked to scientists, though, who say, we've been looking for so long. You mentioned 100 million planets. And they almost argue that because we haven't heard anything, that there must be nothing there.
No, that's a false argument. Look, that's like going to Africa looking for, big mammals with long noses that can pick up peanuts and quitting after you've examined one city block's worth of real estate. And that's equivalent to the fraction of our own galaxy that we looked at. There are roughly a trillion, to go over those numbers again, there are roughly 1 trillion planets in our galaxy. There are 2 trillion other galaxies we can see, each with 1 trillion planets. To say, oh, well, it's all sterile is a bit self-centered.
Dr. Kasting, in looking at Enceladus's plume, how fast are the gases escaping? Is this something that will go on for millions of years?
Oh, my understanding is that plume will keep going. You know, there are 4 stripes on Enceladus' south pole that are called the tiger stripes, and the plume is coming out from there. So this plume has been there for the 10 years that Cassini has been up. You know, what you want to do is actually try to encounter that plume at slower velocities. It's a spacecraft moving fast through it that makes it difficult to measure. So it would be nice to go back and go through that plume. I think it will be there, and go through it more slowly.
And very quickly, I'm familiar with the binary stars where the one rotates around the other. When you get to this triple star system with Alpha Centauri, what's the planetary motion or the star motion that goes along with 3 of them?
The 2 bright ones, Alpha and Beta Centauri, are close together and orbit pretty quickly. Proxima Centauri, the M star, which has the planet around it, is far away, and it's actually not even entirely certain that it's gravitationally bound.
Okay, interesting. Thank you very much. Mr. Chairman.
Thank you, Mr. Byer. The gentleman from Oklahoma, Mr. Lucas, is recognized.
Thank you, Mr. Chairman. And I agree with my colleagues. This is a fascinating topic. It's caught the attention of our constituents back home. And from that perspective, let me ask the panel. We've invested on the federal level, whether it was Hubble before in the first generation of space telescopes that caught the public's imagination, or the money we're spending on James Webb. Our European friends and a number of folks in Chile and a variety of other places spent substantial monies that can be used in this exoplanet search work. Visit with me for a moment about the technical requirements. If we are successful in finding a blip, a squeak, a whatever, how we go forward with the next generation, what is required to go to the next generation. Do we ultimately have to tie every telescope that's on the surface of the planet together, computer-wise, to create that field to observe from? Where do we go in the next generation? Which, if we encounter something that's defined as a likely, the public will become very enthusiastic for.
It's my belief that most of the technologies that we're going to deploy to answer this question have not yet been invented. I really believe that what's going to happen as we go forward and look, for example, at microbial life in the solar system, or we look at exoplanets and look at the first emissions of atmospheres using James Webb and other of our best telescopes we're building now. There's innovators right now that are developing next generation, highly sensitive spectroscopy type of tools that even within a few years will be proposed to one of our announcements of opportunity at NASA or elsewhere, and really will cause that kind of rapid rush forward that is really typical of this kind of research. So for me, that's one of the amazing parts of this research, is that it causes so much innovation. You know, the first planet around another star was announced in 1995. You know, I mean, it's a little bit over 20 years. Look where we are today. Look at the tools we're using today. We never knew to look at dwarfs, as, you know, like we didn't know how. Right, and so this is where kind of the mother lode is of this. So for me, it's really that progress that makes it so exciting. Yes, there will be a lot of innovation.
Could I make a comment on that? You know, we've heard about James Webb Space Telescope, which is this huge, wonderful telescope that's going up next year. But James Webb will only be able to take spectra of the transiting planets, which is a small fraction of the planets out there. Most of the nearby stars, the planets don't transit. So what we really need is big direct imaging telescopes of the same size as JWST, or maybe even a little larger, but especially equipped with coronagraphs or star shades to block out the light from the star so that you can see the planets orbiting around it. And so that's my own personal interest. I think that's where we have the best chance of finding life.
In the case of intelligent life, of course, every telescope in the world would be aimed in the direction from which the signal is coming. You can be sure of that. But in terms of what's coming down the pike for instrumentation, the Europeans, mostly the Europeans, are building what's called the Square Kilometre Array, both in South Africa and Western Australia. And that's an instrument that's 10 times larger than Arecibo, which is already 10 times larger than what we're using. So that kind of thing would allow us to follow up and find other signals coming from other places. Usually in astronomy, if you find one of thing, that means you're going to find a lot more rather quickly, partially because you know what you're looking for.
Doctor.
Thank you, and I want to thank you for asking that question. I want to tack on to the technology development that we can't even, maybe not even anticipate at this point. Just the techniques that have been developed to find these planets were things that were not anticipated early on. So the Spitzer Space Telescope, which I mentioned, was central for discovering the TRAPPIST planets. When it was launched, it was not designed to do what we did with it. It was not designed to look for exoplanets and measure these transits, and yet it's been one of the most successful outcomes of that mission. And so I think when you give people tools, they discover new ways to use them and ways that we may not anticipate that could actually do more with the investments in these facilities than we could have expected.
Thank you very much. Your comments present optimism at its very best, and it's fascinating to think that we have our echo chamber out 70 years, so to speak, light years. With that, Mr. Chairman, I yield back.
Thank you, Mr. Lucas. And the gentleman from California, Mr. Rohrabacher, is recognized.
Let me first apologize that I came in late. As you know, we have several, they're only scheduled at the same time. I will be looking at your testimony, your written testimony, and I want to thank the chairman. We have a chairman who's a visionary, and we're lucky to have him there to be able to touch on things like this that other, I might say that other chairmen that I've served under were not quite as willing to go into these type of areas because they were afraid of ridicule. I mean, you can see it. Oh, they're out searching for aliens in outer space, and we need to have a very serious and discussion on your mission and what's going on. And let me just note that I have been a longtime supporter personally of developing telescopes, of deep space missions, as well as astronomy in general, and knowing that with astronomy we can determine truths that are happening out there that affect our knowledge even of molecular structure and how it works here on the land. So, and I will have to tell you that my support, they didn't have to twist my arm in order to get my support for those projects. I have first of all, let me just ask this, and then my son, I have a 12-year-old son, and he would just die if I did not ask this question. With what we know now and how you have now just expanded our understanding of how far reality goes out from our planet, with that in mind, here's my son now, is time travel possible?
If you're willing to go to the future, you can do, and you're doing it right now. Going to the past seems to violate some basic tenets of physics. There's a book out about time travel, a new one. Actually, your son may want to read it. I think it's by Gleich, the same guy who.
But actually, some of the things you're doing now and you're studying will give us understandings maybe 100 years from now on something that may be an incredible breakthrough for humankind, like the idea that it's possible to have time travel.
Yeah, well, one should never discount the possibility of new physics that changes one's attitude. But at the moment, I would bet against it.
Yeah, if I could comment, I don't know about time travel, but I always thought that travel to other stars was impossible. But, you know, there's a private group out in California called Breakthrough that is studying Project Starshot. They want to send a spacecraft to Alpha Centauri, and so that's something that I never thought was going to happen, but it's not impossible.
Not impossible, not impossible?
Time travel, I would hedge against. I think I agree with Dr. Shostak. But certainly the excitement about space travel, that's something that is very recent and honestly technologically very possible.
The short answer is I don't know, but the one thing I've learned in looking at science is never discount options.
Okay. Now, again, I'm going to have a plebeian approach to my questions, and that is, I watch the History Channel, and I watch various things that are presented on about things that we may have spotted on things like Mars, where there are objects that appear to be walls. Are all of those objects, have you just written them off and they're not products of other civilizations?
I think it's safe to say they are not. I get emails and phone calls every day from people who claim they have good evidence for aliens visiting the solar system. And I wish it were true. I wish it were convincing. It would be job security for me, after all. But if you look at most of these claimed artifacts found on Mars by people who go through, for example, the rover photos and so forth. I mean, they find, you know, little statuettes. They find critters like lizards. They find ocean-going creatures. There's also a Nazi helmet. This may be news to you that the Wehrmacht actually went to Mars. All of this are examples of pareidolia, which is to say, like looking up in the clouds, you can see almost anything you want.
You rule out that any of these things, objects that we see, are indicating of some life form?
There may be life on Mars, but I don't think it's manifest in these images.
What about you, sir?
I agree with what Seth said, and the images are not convincing. I don't see as many as Seth does, but I'm interested in looking for Mars in the subsurface, looking for life in the subsurface.
And?
Yeah, I would also say I'm not convinced. I mean, we have evolved as a species to have incredible pattern recognition powers, and so we find patterns in lots of things. Outstanding claims require outstanding evidence.
Same here. Basically, I've been personally involved in more than one of these instances where something comes up, and we tend to deploy a great scientist to go look at this. In some cases, it's just a camera effect. You know, you look at your own pictures and you see kind of weird things just because of how camera works, and sometimes it's like what he says. You know, it's the lion in the clouds, that type of thing.
Well, I know we're getting a great deal of understanding from your labor and your effort that you're putting in to this project, a great deal of a better understanding of the nature of the universe. And we appreciate that, and we appreciate your advice to us on how to be realistic about that as well. So thank you very much.
Thank you, Mr. Rohrabacher. The gentleman from California, Mr. McNerney, is recognized.
Well, again, I thank the chairman for holding this hearing. Dr. Sostak, about SETI, you mentioned that SETI is getting better at identifying targets and improving, and the equipment to be used is also improving. Could you elaborate on what's improving in terms of the detection and the equipment that's used to survey?
Yeah, to some extent there's an improvement simply in raw sensitivity, that you can find weaker signals. But that depends on having lots of antennas. That means putting up lots of physical structure. Aluminum hasn't gotten a whole lot cheaper in the last 20 years. So that's a very slow improvement there. The big improvement is in the receiver technology, where instead of looking at one star at a time, which is what we've done, when I say look at a star, of course you're assuming there may be planets around it that have somebody with a radio transmitter. Instead of looking at one at a time, you could, in fact, look at tens, hundreds, even thousands of stars at a time with enough computer processing capability. And, of course, that capability is coming down the pike. The other thing that we're beginning to deploy is what's called machine learning. This is where you use massive computing power to search for all kinds of patterns in the signals. Today we have sort of a dedicated machine that looks for one kind of pattern. It's sort of like, I don't know, having hearing where you can only hear one note. You're not going to really get a lot out of a symphony. But if you can, you know, use machine learning in this case to broaden the kind of thing you could recognize, then that will all speed up the search.
What's and I'm not sure who to ask this question, but what's the risk of contaminating other planets with nearby planets, Mars, and so on, with Earth biology?
We, for missions to places where we expect that could harbor life or any organism, such as Mars or Europa, we use protocols we refer to as planetary protection. And so basically what we do is go look at it in both ways. The first one is we don't want to destroy an experiment, so we actually take tremendous efforts to make sure that we don't bring a lot of our life there or organisms, and so we don't destroy an experiment. The other thing, we also want to make sure if we found something and brought it back, and that's going to be important once we start bringing back samples from places like Mars and so forth, we want to make sure that if there was life in there, that it's not kind of the equivalent of a really lethal virus. So we, the kind of mechanisms that we would use for such bacteria or viruses, like we would use in this context. So we have mechanisms that we use for every one of those missions, both classification and also how we actually build the missions and land them and so forth.
Yes, Dr. Kasting.
Could I add just a comment to that? I mentioned in my testimony that Cassini is going to crash into Saturn at the end of the summer. NASA's doing that intentionally for planetary protection reasons, because they don't want, after they lose control of Cassini, they don't want it to crash into one of Saturn's moons or the rings.
Another question is, with all the new information on exoplanets, and is there a way to classify all this information, or are we still sort of ad hoc trying to figure out how to put these things into some sort of order?
So there are several groups in the exoplanet community that have gotten together to develop websites, databases that organize this information. I mentioned earlier in my testimony the University of Puerto Rico at Arecibo has a exoplanet habitability laboratory, and they've developed criteria to assess the habitability of various planets. There are a number of great resources that compile the data on these 3,000 plus exoplanets. And again, those resources are publicly available, and so I often have my students do research projects to explore these catalogs and come up with their own measures of habitability and potential for life.
So is for someone that's not immersed in this issue, is there an ability to go to that resource and understand what's happening, or is it still pretty foggy?
No, and what I can do is I can put in the written testimony some of these resources, but they actually have the sort of demonstrations on how to use the data. They're extremely well designed, and they have gotten a lot of interest from the public.
Very good. All right, Mr. Chairman, I'll yield back. Thank you.
Thank you, Mr. McNerney. Without objection, the ranking member, Ms. Johnson, is recognized for an additional question or two.
Thank you very much, Mr. Chairman. This really has been an exciting hearing, especially as we look toward the future. And I'm sorry Mr. Rohrabacher had to leave. Speaking of his 12-year-old son, it really is the thing that excites young men, young people, when we can look to the future and start to explore the unknown. And in 30 years, we might know a whole lot more than we know now. And my question really is to the panel here. What do we do as a Congress to make sure that in 30 years we're on top of what's going on in the universe? How do we move forward? How well equipped will we make sure that our young minds be stimulated and be interested in this area? I'm so grateful for those who came before us who made it possible for today, and thanks to all of you. But we have a challenge, Mr. Chairman.
Okay. Thank you, Ms. Johnson. Let me respond very quickly, and I think most members know that we are fortunate to have within our committee's jurisdiction STEM education, or many aspects of STEM education. And in fact, I believe the first two bills that President Trump signed last month were two STEM bills that were produced by this committee, and I was over there for the bill signing. And we will continue to go in that direction. The other thing I think that is good news for us is that most agencies had their budgets cut. NASA was one of the few agencies that did not incur any cuts. So we have an administration, I think, and a Congress who is very interested in space and what's out there. Let me thank our witnesses again today. You all have just been fascinating and informative, and we appreciate your taking the time to be here. Clearly, on the basis of the questions you were asked, there's interest across all members in what you're doing and the different things that you're doing as well. We heard things today we haven't heard before, and that's always enough to keep us going and have future hearings on the subject as well. So thank you all for being here. We stand adjourned.